Chapter 15, sample problem number 16. Wood blocks that have different masses and different volumes are floating in water. On top of these blocks are additional masses as shown. And we are asked to rank the buoyant force exerted by the water on the wood blocks. Let's take that generic situation where we have a wooden block with mass capital M, and floating on top of it is some sort of little weight, and I'm going to call that little m as that mass. And we say, what forces act? Well, on little m, there is its own little weight, m times g, pointing downward, but there is, of course, some sort of normal force which is holding it on top of the wooden block and not letting it pierce. And then on the wooden block, well, that normal force pushes down. There's also, of course, the weight, the earth pulling down. And finally, there is a buoyant force pushing up. And we know that for each of these guys, the force on the wooden block has to be equal to the mass of the wooden block times its acceleration, which is 0, so it has to be 0. And the force on the metal has to also be the mass of the metal block times acceleration, which is 0. But looking at our pictures, we have that the sum of the forces on the wooden block are gravity pointing downward, and a buoyant force pointing upward, and a normal force pointing downward. And Newton's second law says all of those have to sum to 0. And likewise, looking at the metal, the normal force pointing upward we add the weight acting downward, and that also has to equal 0, which tells us that the normal force has to equal the weight of the metal block, the metal thing on top, which is sort of a long-winded way to get to what we expected, which is that what really matters is the total weight of these two things. Because if I go back over to this equation, I end up being able to say that the buoyant force has to be the weight of the wood block plus the normal force but we just found that the normal force is the weight of the little guy, and so we're left with that the buoyant force is the sum of the masses times g. And since g is the same for everybody, it's really just the sum of the masses that matters. So if I go through here, I can say, well, the sum of the masses here is 30, and the sum of the masses here is also 30, but the sum of the masses here is only 20, and the sum of the masses here is 50. So we immediately say that D is clearly more than A or B, which are the same, which is more than C.